All right, today we're going to peel back the curtain on something you can't see but is all around us, the invisible landscapes of energy created by electric charges. And trust me, this isn't just some abstract physics concept. It has some seriously practical, even life-saving applications.
So let's kick things off with a question that sounds like it breaks the rules of reality. Picture this. You're sitting in your car or on a plane during a massive thunderstorm. A bolt of lightning, millions of volts, strikes the metal shell right around you, and you're totally fine. How on earth is that possible? Well, stick with me, because by the end of this, you're going to understand the physics behind that incredible trick perfectly.
Okay, let's get right into it. Here's what we're covering. We'll talk about the invisible electric landscape, what happens with a perfect metal shell versus a sphere of trapped charge, solve a cool Russian doll puzzle, and then see how it all creates a real-life force field.
All right, first things first, we need to get to know our main character for today, electric potential. You know, it's this invisible field that's everywhere there's an electric charge, and it basically tells those charges where to go. The absolute best way to think about it is like, well, electric height.
And here's the key idea, the thing you really need to get. A ball will always roll downhill, right? From a high place to a low place. It's the same exact idea with electricity. Charges naturally want to move from a place of high electric potential to a place of low electric potential. That push, that urge to move, that's what we're really talking about when we say voltage.
Okay, so with that idea of electric height in our heads, let's look at our first case study, a simple hollow metal sphere. And the magic word here is conducting. All that means is that the little electric charges inside the metal can move around wherever they want. They're not stuck in place.
So what do these free-moving charges do? Well, if you remember, charges that are the same, like two positive charges, they repel each other. They want to get as far away from each other as possible. So on a sphere, where's the farthest they can go? The outer surface. They all race to the outside and spread out perfectly evenly. And this one simple fact is what gives us these different rules, these formulas for what the potential looks like inside versus outside the sphere.
But here's where it gets really, really cool. This is the big takeaway. Because all the charge is hanging out on the surface, the inside of the sphere is, well, it's totally flat, electrically speaking. There's no electric hill to roll down. It doesn't matter if you're in the center or right near the edge. Inside that shell, the electric height is constant. It's the same everywhere.
And this graph just shows it perfectly. Take a look. See how that line for potential, the V, is completely flat all the way from the center out to the radius A? That flat line is everything. It means there's zero difference in potential from one point to another inside. No push, no pull. It's a perfectly calm, safe electrical zone.
Okay, that's a conductor. But what if the charges can't move? What if they're locked in place, distributed all through the inside of a sphere? Think of something like a solid ball of plastic or glass. We call that a non-conductor or an insulator. How does that change the game?
Well, it changes everything. The rules get flipped completely on their head. Since those charges are stuck all over the inside, the potential isn't flat anymore. In fact, if you run the numbers, you find something pretty wild. The potential is at its absolute highest right in the dead center. It's actually 1.5 times higher there than it is on the surface.
So let's put them side by side. It's a tale of two spheres, really. On the left, you've got the conductor with its totally flat, safe interior potential. On the right, the insulator has this curved electric hill inside. The difference couldn't be more dramatic. And it all comes down to one thing, whether or not those charges are free to move.
So let's just nail this down. Conductor, charges flee to the surface, inside is one constant potential. Easy. Insulator, charges are stuck everywhere, creating a potential that's actually highest right at the core. You have to get this difference because it is the key to, well, pretty much everything else we're about to talk about.
Okay, you ready for a puzzle? Let's take this up a notch. What happens if we start nesting these spheres inside each other? You know, like those Russian dolls? A charged sphere, inside another charged sphere, inside a third one. How in the world would you even begin to calculate the potential somewhere in the middle of all that?
I mean, it looks like a nightmare, right? Super complicated. But here's the beautiful, elegant secret of electric potential. You don't have to solve it all at once. You can just figure out the potential caused by each shell on its own, and then you just add them all up. It's that simple.
You literally build the answer step by step. What's the potential from the inner shell? Got it. Now what's the potential from the middle one? Okay. And the outer one? Right. Now just add those three numbers together. This incredibly powerful idea has a name. It's called the principle of superposition.
So using that idea, the source material asks a really cool question. Is it possible to rig the system? Can we choose just the right charges and sizes for these shells so that the electric height on the very inner shell is exactly the same as the electric height on the very outer shell?
You'd think the answer would be some horrible long equation, right? But check this out. When you do the math, when you set the potential equations equal to each other, a whole bunch of stuff just cancels out. And what you're left with is this stunningly simple, beautiful relationship. The radius of the outer shell, C, has to equal the sum of the other two, A plus B. I mean, come on, how cool is that? Physics can be so elegant sometimes.
All right, time for the grand finale. This is where we take all these ideas and see how they create a real-life force field. And yep, we're finally going to answer that question about why you're safe in a lightning storm.
So imagine you take a conductor, a metal sphere, or a car, and you stick it in an external electric field, like the massive one created by a storm cloud. What happens? Well, those free-moving charges inside the metal react in a flash. All the positive charges get shoved to one side, and all the negative charges get shoved to the other. And this separation of charge, it creates its own electric field, an internal one, that points in the exact opposite direction of the big one outside.
And the result? It's like a perfect tug of war. The internal field the conductor creates is exactly as strong as the external field it's sitting in. They pull in opposite directions and completely cancel each other out. So the total, the net electric field inside that conductor goes to 0. Not almost 0, not really small, exactly 0. It's a perfect shield.
And you can see exactly what that looks like here. Those lines represent the electric field, the path a charge would be forced to follow. And look, they can't get through the conductor. They literally have to bend and warp their way around it. They hit the surface and just stop. They are totally blocked.
And that brings us right back to the beginning. The metal body of your car, it's a hollow conductor. That massive electric field from the lightning strike, the charges in the car's metal body rearrange instantly to create an opposing field that cancels it out perfectly. So inside the car, it's a calm, zero field, constant potential zone. And if there's no potential difference, no electric hill, then there's no reason for current to flow. And no current flowing through you means you're perfectly safe. That's a Faraday cage doing its job.
Now, this perfect shielding works like a charm for static fields, fields that don't change. But that should make you wonder, right? If conductors block electric fields so well, how do things like radio waves, Wi-Fi, or your wireless phone charger work? They send energy right through the air, sometimes even through walls. How do they get around this perfect shield? Well, that's a whole other story, one that involves changing dynamic fields, and we'll have to save that for another time.